All right. So, loci in the complex plane. Now, if you have a look at the textbook, you'll notice these questions aren't included in the textbook. And so what Hazy's done is they've added these questions to the online version of the textbook because they've sort of made some adjustments to the curriculum. And so the worksheets that I've included in your notebook, so worksheet 1 and worksheet 2, they're from the Hazy online resources. All right. Worksheet 1 is, worksheet 2 is from an alternative textbook. Both of them are relevant, and there's even worksheet 3. Yeah, so worksheet 2 and 3 are from an alternative textbook. Worksheet 1 is from the Hazy textbook, and basically you're expected to be able to do all of it. So we'll go through the examples here for loci in the complex plane. It's also
1, 2, and 3.
Worksheets 1, 2, and 3. Yep. We'll go through the examples for loci in the complex plane. It's also often called complex sets. So we'll just get straight into it. The first one we have is consider Z is 2 cis of 0 and W is, did you forget your notebook?
Yeah.
Oh no. Z is 2 cis of 0 and W is 3 cis of pi on 3. Okay, find the distance between them. So just in terms of the eigenplane, what's going on here, we have Z, looks like this, okay? It's just in the real direction with a magnitude of 2, and this one is has an argument of pi on 3 and a magnitude of 3. And so we could use like a cosine rule to find this distance between them, right? We've got a squared is b squared plus c squared, take 2bc cos a. So we could do that, that would be an appropriate way to find the distance. But I think let's look at how we can use this procedure here. If we think of vector operations, like if this is z and this is w, then this vector here, all right, is going to be minus z, such that it is in that direction, minus z plus w, or we can think of it as, w take z, that's going to give us this vector. And so then the distance between w and z is the modulus of w take z, or the modulus of z take w. All right, either way, you're just saying what's the length of it. Doesn't matter which one we make the negative. Okay, so that's the formula we're going to use. The distance between two vectors or between two complex numbers on the eigenplane is just the modulus of the first one take the second one. So we can write it out like that. We've got 2 cis of 0, take away 3 cis of pi on 3. Now, polar form is useful for when we're multiplying and dividing complex numbers, but Cartesian form is useful for when we're adding and subtracting them. So the first thing we're going to do is convert them both to Cartesian form. So the long way, the quick way is just plug that in your calculator. All right, the long way is to think, all right, that becomes cos of 0 plus I sine of 0. All right, and then over here we'll have 3 cos of pi on 3 plus I sine of pi on 3. All right, and cos of 0 is positive 1 from our unit circle, so we have 2 there, and sine of 0 is 0, so 2 times 0 is 0. So this complex number is just 2 in the real direction. And we've exhibited that there, that's all it is. It has a real part of 2, the imaginary component 0. So that's that complex number. Then we have take away, and we've got this one now. Cos of pi on 3 is root 3 on 2, half. Cos of pi on 3 is half, so 3 times a half is 3 on 2. And sine of pi on 3 is root 3 on 2, so 3 times root 3 on 2 will be 3 root 3 on top of 2, and the I belongs there. Okay, then what we would do is we've got, here's Z in Cartesian form, here's W in Cartesian form. We're just going to collect the real parts and the imaginary parts. So 2 take 1.5 gives you half. And here's the imaginary component, 3 root 3 onto I. And now we're just doing modulus. Modulus of a complex number is the square root of the horizontal component squared plus the vertical component squared. All right, so evaluate that. 1 on 2 squared will be 1 on 4. Here this is going to be 9 times 3, that's going to be 27. On top of 4, they have the same denominator, so we have 28 on 4, and 28 divided by 4 is 7, root 7 units. Okay, and of course we can just type that into our calculator as well. If you type in, you know, the modulus of this in your calculator, this is what it's going to spit out. So we can verify all of that using our calculator. What's the algebraic process? We converted it to Cartesian form. Again, you can do that part using your calculator. We collected like terms, form the modulus of this complex number in Cartesian form. Okay, next what we're doing with complex sets or loci in the complex plane is we're illustrating regions such that a relationship maintains. So if we have a look at our first one, illustrate the following. So we have the modulus of z is larger than 1, and the real part of z is positive. Alright, so that's what that means. The modulus of it, the size of it, is larger than 1, and the real part has to be positive. So if you consider your eigenplane, firstly, if the modulus of z is larger than 1, it means it would have to be outside of a circle that has a radius of 1. Okay, so that's the first thing, is that it has to be outside of that circle, not on that circle, and the way we illustrate that is with a dotted line. That illustrates it goes like asymptotic, goes up to it but doesn't touch. And then the real part being greater than 0, well, this is our real axis, and so if the real part's positive, then we're illustrating this region here and beyond, okay? It doesn't exist for negative values, and it doesn't exist for values that have a modulus less than 1. Okay? Alright, so that's the first one. Okay, on to the second one. Now for these, I'm going to perform the algebra, but you will notice the more and more you do them, you'll pick up quick shortcuts of identifying what's the relationship I'm required to draw here. I'm not going to, we can explain them maybe on Thursday, but for now I just want you to perform the algebra. So we have this relationship here that we're asked to illustrate. So we have the modulus of z, take 3 plus I, equals 4. Alright, the first thing we're going to do is define the complex number z. So we'll have let z equal a plus bi, or x plus iy. Probably x and y is better because we're going to use x and y on the Cartesian plane. So let's sub that in. We have x plus iy, take 3 plus I. We're finding the modulus of that equals 4. Alright, now I'm going to collect the real component and the imaginary component together. And we know the modulus of it is going to be, because that's what we're asked to perform, the modulus of it, that's going to be the square root of the horizontal component plus the vertical component equals 4. And then square both sides. Who can remember what is that?
Circle formula.
Well done. That's the equation of a circle. So a circle, all right, has the formula x take a squared plus y take b squared equals r squared. But that circle has centre AB and radius r. All right, so that means if we're going to sketch this circle, its centre is positive 3 and negative 1, and it has a radius of 4. So on the eigenplane, all right, label our real and imaginary axes. And we have a centre of positive 3 and negative 1. That's the centre. And it has a radius of 4 units. And so the way I'm going to draw that is I go, okay, it's going 4 units that way, so that's the point furthest to the left. 4 units that way, so at minus 5. 4 units that way, so at positive 3, and then 4 units that way would take you to positive 6. And then we're just drawing a circle. Better than me on grid. And so we've illustrated that this relationship is true. Okay, maybe just really quickly, I can point out, I've performed the algebra to show you that this is the relationship that maintains, but have a look at this. Minus 3 plus I, and what have we gone? We've gone across 3, down 1, circle with a radius of 4 units, okay? So whenever it's equal to a real number, we're just drawing a circle. The next example is going to be slightly different. So we've got A, B, C. Now, also what it technically means is any complex number z drawn from this location has a radius of 4. So here's the location. Any complex number drawn from that location has a modulus of 4 units. Okay, so that's what that means. Okay, onto the C. We have the modulus of z plus 2 is equal to the modulus of z take 1. Similarly, let's perform the substitution for z. So we're going to have x plus iy plus 2 equals x plus iy take 1. And we want the modulus of both of those. Collect the real components. Perform the modulus formula. Sorry, let's go rid of it. Alright, square both sides. Cancel y, it's on both sides, expand both sides. Look at this, we love algebra in specialist maths, and it's lots of fun. X squared on both sides can cancel, and then we're just going to collect the x's, so I'll add 2x to both sides, we'll have 6x. Take 4 from both sides, we'll have minus 3, and we'll have x is minus 3 on 6, or negative half. I've raced through that, so I'll give you a chance to scribble it down. So that's all right, everybody? Followed along with that algebra? Yep. Okay, so what's the question asked us to do? Sketch this relationship. What's this relationship? X equals minus half. How would you sketch that on the Cartesian plane? Well, here's x is 0, here's x is 1, here's x is minus half, and so this is the line x equals minus half. Now, let's think about what does it mean, okay? It's saying that the complex number drawn from minus 2, the modulus of the complex number drawn from minus 2, so here's minus 1, let's put it up, here's minus 2, so the modulus of the complex number drawn from minus 2 is equal to the modulus of the complex number drawn from 1. Okay, so notice if I draw a complex number here and here, they have the same modulus. If I draw it here and here, they have the same modulus. So what's going on? This, the visual part of it, if we don't perform the algebra, it's the equation of a vertical line directly between negative 2 and positive 1. All right, so that's C. And we've got 2 more. So let's follow on with that illustration logic for this next one. All right, so if we talk about 3, we have to illustrate this relationship. We have the modulus of z take 2 plus I is equal to the modulus of z plus 3 take 2i. Now let's just plot those points on an eigenplane. So 2 take I, so across 2, I'm going to have to draw some numbers up, and then down 1. That's the first one. And then the next one is take 3 up 2. So we'll go 1, 2, 3, take 3, and then up 2 here. All right, so if the modulus from those points is equal, what it means is it's the perpendicular bisector between. Okay, so that's what it's going to look like. That's a pretty clumsy drawing though. I want to be more precise, which means I'm going to perform the algebra for this relationship. All right, so we can observe that it's true that, you know, the modulus there is equal to the modulus there, the modulus there is equal to the modulus there. So let's perform the algebra. All right, so collect the real and the imaginary components. Into the modulus formula, and you don't need to write the square root component if you don't want to, because we're square rooting both sides. Then we're just going to expand everything and collect like terms. So it's going to be quite long here with x squared take 4x plus 4 plus y squared plus 2y plus 1 equals x squared plus 6x plus 9. Okay, once we expand it, we can see we've got x squared on both sides of the equation, y squared. All right, and we know as well, like based off my visual here, this is the equation of a line. So that means I'm going to get y on one side, y equals mx plus c. That's how I'm going to try and manipulate this algebra here. So what I might do, I'll bring these y's over to this side. So let's just state what we have at the moment. Do it minus 4x plus 4 plus 2y plus 1 equals, and we've got 6x take 4y, plus 9 and plus 4. I'll just collect that, that'll be positive 13. All right, so we want the numbers and the x's on the right side and the y's on the left side. So I'm going to add 4y to both sides. That's going to give me 6y here. And we've got 4 plus 1 will be 5. And then 13 take 5 is 8. So that's going to be our constant over there. And we're going to add 4x to both sides. That's going to give us 10x over here. 10x plus 8. And then divide both sides by 6. So we'll have 5 on 3x plus 4 on 3. Okay, so the equation of this line then, let's go back to graphing lines. Okay, the y-intercept is 4 on 3. So if here's 1, 4 on 3 is 1 1/3, so it's just above it, like it's 1/3 of the way between 1 and 2. That's the y-intercept. And we have a slope of 5 on 3. Now it's positive. And remember, slope, like think of it, always think about this relationship. y2 take y1 and x2 take x1, which is the same as change in y and the change in x. Now we have a slope of 5 on 3, which means the x changes by 3. So from there, we're going across 3, up 5. We plot that point and then draw a line through those 2 points. Across 3, up 5, or if you're moving to the left, across 3, down 5. All right, really good. So that's 3. Happy with 3A? Excellent. 3B. And 3B, we have illustrate this. We have an argument. We have the argument of z plus 1 plus I is equal to pi on 3. Yeah, we just have it's equal to pi on 3, don't we? Yep. I thought, can we change that a little bit? I wanted to illustrate a region rather than a direction. So let's just express it like this. 0 is less than, and then we'll go less than or equal to. Okay, so that we can illustrate both. So I'll fix up that example in the online version. All right, so what that means is we're drawing a complex number from this location. So it's across one, down one, across one, down one. So we're drawing it from here, and the complex number drawn from this location has an argument that lies between 0 and pi on 3. So 0 is here, and we're not including 0. And we'll draw an arrow to illustrate we're not constraining the modulus. And then pi on 3, well, that's pi on 2, you know, that's pi on 4, so pi on 3 is about here somewhere, and we are including that point. And so this is the region that satisfies that complex number. Okay, maybe I can just talk really clearly. You're probably going, hang on, that says +1 plus I. How come you're going to, you know, -1 take I? So think back to when we're talking about transforming functions. Okay, particularly like if I'm talking about the roots of a function, so what would be a good example? Let's talk about the quadratic x take 2 squared. That means you go to the right 2 units. And the reason is, like, if you think of, okay, what are the roots? You know, you square both sides, and then you solve this, you have x equals 2. All right, the root is 2. So, similarly with this one, what's going on is we're treating it like it is z, either take 1 plus I, all right, maybe here's a better way, it's take -1 take I. All right, such that the root is -1 take I, right? If you distribute this negative, then you get both of those terms positive, right? So that's probably the best way I think to explain that. Basically, you're just doing the opposite of what it says. Excellent. Okay, so that is our loci complex sets. Now there's copious quantities of questions for this exercise. So yeah, we have a bit to do before Thursday, and on Thursday we'll do a summary together. Leading into the holidays, I'll have some pracky tests for you, and so study. So there we go.